Hello, today we present our project TESGNN, which stands for Temporal Equivariant Scene Graph Neural Networks for Efficient and Robust Multi-View 3D Scene Understanding. A scene graph is a structured representation of a scene, typically used in computer graphics, robotics, and computer visions. It organizes objects and their relationships in a graph format, where nodes represent objects or entities in the scene, and edges represents the relationships between objects. And scene graph can be applied in computer vision to help with semantic understanding of image and video, or can be applied in robotics to use for spatial reasoning, task planning, and scene understanding in robotic perception, and can be applied into 3D graphics and simulation to organize hierarchical objects structures for rendering and physics simulation. Existing work in scene understanding often struggle from making prediction in case of transformation, such as rotation and transition. So as you can see in the image here, so in a different angle, the model detects the objects as a shelf, but if we rotate it in a different viewpoint, then it detects the objects as a wall. And additionally, existing work often require more data augmentation during training, and it has slow conversion and large size of model if we use VOM-based semantic map for scene understanding. And existing work methods also focus on either scene graph generation or graph matching, without having a combined method for both of these. Graph matching typically assumes that we would have a noise-free and ground-truth scene graph beforehand, and this assumption limits the real-world applicability due to the ambiguity and noise in the predictions for scene graph generation. Therefore, we propose TESGNN comprising of two components. The first component, Equivariant Scene Graph Neural Networks, ESGNN, which extracts scene graph from 3D point clouds using an equivariant GNN. And we use equivariant graph convolution and feature-wise attention for rotational and translational invariance. And ESGNN deliver high accuracy, faster training, and lower computational costs. And based on our understanding, we are the first to apply equivariant GNNs for scene graph extraction in 3D. And the second component is temporal scene graph matching, which will fuse local scene graph into a global representation via graph matching, which match the node based on embedding similarity using ESGNN as the backbone. This method improves multi-view scene understanding and outperforms existing extractor and has the potential for enabling multi-agent coordination and navigation in dynamic environments.
Our framework is given in the figure on the screen right now. So we set the point cloud and feed it through the geometry segmentation. Given that result, we use it to initialize our first graph. Then we do the massive passing through the ESGNN layer to get the vector representation. After that, we feed it into the decoder for the graph for each frame. And then given the different graph from different frame, we fuse it together through the temporal layer to get a global scene graph. Our method achieves significantly lower time for conversion. Here we have somewhere around 5,000 steps compared to 10,000 steps of the scene graph fusion. We also do the application study, and we also test on the joy at GNN, which have the image encoder, and we also had like the similar result. Our method not only surpass the time conversion, but also had the competitive result for the prediction that you can see on the screen. Besides, we also had the lower time for the inference, also the less number of parameters of the model, which enable the chain for implementation this one in the real scenario. For more detail, please check out our paper and our GitHub for the code implementation. Thank you.